What is Hawking radiation? On 14th of March 2018, the world lost Stephen Hawking, one of the most brilliant minds of our time. His passing marked not only the end of an extraordinary life, but also a moment of reflection for humanity. At his funeral, scientists, students and admirers from across the world gathered to honor a man who, despite immense physical challenges, expanded our understanding of black holes, time and the cosmos itself. Beneath the ancient stones of Westminster Abbey, Stephen Hawking rests among Newton and Darwin, minds that reshaped humanity's understanding of the cosmos and of life itself. Well, fittingly, the date coincided with Einstein's birthday, a poetic passing of the torch. In Westminster Abbey, where Hawking is laid to rest alongside Newton and Darwin, his tombstone bears a single profound equation, the formula for the entropy of a black hole. Well, this was Hawking's gift to science. The discovery that black holes are not eternal prisons but thermodynamic objects with entropy and temperature, radiating energy through what we now call as Hawking radiation. Well, that simple looking equation is the central idea of today's video, and engraved in stone, this equation unites gravity, quantum mechanics and thermodynamics, the pillars of modern physics, and stands as a symbol of Stephen Hawking's quest to understand this universe. Let us dissect the equation and understand what it is. Well, as you can see, if I take this equation as a whole, the T is basically the temperature of the black holes measured in Kelvin usually. Then you see something which you are all aware about, the h bar, which is called the reduced Planck's constant. That means we are dealing with something which are called quantum effects or quantum mechanics. Obviously, this 8 pi is a kind of a derivation which is out of the scope of today's video, but you can understand that this arises from the spherical geometry of black hole and how the surface gravity is converted in temperature. The G is the good old Newton's gravitational constant. The capital M, well, this is the mass of the black hole, and this you all know is the Boltzmann's constant coming from thermodynamics, and the C is the speed of light. Taking all these parts in this equation, what we can tell is that this equation says that a black hole is not completely black, but there is something which radiates a kind of a temperature. And smaller the mass of the black hole, the hotter it is, and so on. Now let us take a close look in all of those equations, or rather the components of the equation. So what we can see from Hawking's equation is that it actually links all the great constants of nature. And this brings us to a profound implication and understanding. H bar, which was actually derived by Max Planck, is the reduced Planck's constant, and it shows that Hawking radiation arises from the quantum effects which are near the event horizon of a black hole. We all know that c is basically the invariant speed of light coming from special relativity. That means this equation also takes in account the space and time and its relativistic effects. G, the classical Newtonian constant, or the constant which is used by Einstein in general relativity, effectively shows that also this equation heavily depends on the space-time curvature and the black hole's event horizon. And then comes Kb, which is the Boltzmann constant, and this suggests that this converts the energy of the radiation into what we call a temperature. So all these four constants actually suggest this, that Hawking's equation actually weave together, or it is trying to combine quantum mechanics, Newtonian gravity, special theory of relativity and thermodynamics in one single formula or a one single equation. And this has changed the way we look in black holes, which was prior to Stephen Hawking during the time of Einstein, and now black holes are totally a different story. Now this equation actually created a profound implication in terms of understanding black holes, quantum gravity and everything. Now what are the implications? Now first you see that Hawking radiation first showed, as I have shown you, that the quantum effects cannot be ignored near strong gravity. That means there are quantum field theory or quantum particles and antiparticles that create and annihilate. And black holes, it is one of the situations where quantum mechanics and general relativity, they interact explicitly. This is the first important implication, that quantum effects cannot be ignored, however negligible they are. The second implication is that through the first law of thermodynamics, you know that the temperature implies that black holes should have an entropy. And this entropy is somehow different, and it is proportional to the horizon and entry area. And this led to something which is called the famous Bekenstein-Hawking entropy, and the equation looks something like this. Now again, explaining Bekenstein-Hawking entropy will take another time and another video, but what we can understand from here is that just like any ordinary system, like a gas or a star, black holes are not entirely black, they do carry entropy. So that is why the left hand side I have shown certain small icons to denote quantum effects, and on the right hand side you think a lot of equations, etc., which actually denotes that they are not entirely black, they carry entropy. That means they represent a measure of certain hidden microscopic information. This is the second implication of Hawking radiation. Well, the third implication is even greater, because the equations includes all four constants that suggest there might be a very deep underlying theory unifying quantum mechanics, gravity and thermodynamics. Now many researchers see that this is a glimpse towards uniting a quantum gravity, even though we do not have a complete theory till now. And the last is even more important, black hole evaporation, because as you have seen that black hole have temperature, they radiate, and as they radiate, black holes eventually lose mass and they eventually disappear. Now this challenges the classical ideas that black holes trap everything forever. No, they evaporate and the mass actually gradually disappear. Now this is something which is very new, which a lot of physicists found it difficult to accept, and here are a few of the phases which actually starts. So phase 1 is basically this classic growth phase where the black hole interacts with the environment, accreting matter, merging with other black holes and so on. Then comes the Hawking radiation part. So in an isolated black hole far away from matter, Hawking radiation becomes important. The black hole slowly loses mass, but the process is extremely slow for stellar mass or large black holes. And then you can see what is called accelerated evaporation phase. As the black hole shrinks and shrinks and shrinks, Hawking radiation intensifies, since the radiation power is inversely proportional to the square of the mass. So the evaporation speeds up and the black hole becomes hotter and more luminous in the final stages. This evaporation continues, and further we find down what is called the end game, or the quantum gravity phase, where near the Planck mass or the Planck scale, Hawking's semi-classical description breaks down. So 1, 2, 3, 4, these are the 5 phases in which the black hole accretes matter, then goes under evaporation, evaporates, and then comes what is called a cosmic silence. So as you can see that there can be 2 phases: complete evaporation in radiation, a stable Planck mass remnant, or some new quantum gravity effect, string theory, etc. This, to be very honest, this phase is still unknown to physicists. Now what is more important is that as the black hole loses the mass, and it shows through Hawking radiation that the entire black hole slowly evaporates, this led to a very controversial and important phase of science, which is called information paradox. What is information paradox? That we are going to understand in the next part of our video. Now we have seen earlier that black holes radiate an energy, and this is known as Hawking radiation. Now because energy is equal to mass through Einstein's famous E equals to mc square, that means the black hole loses mass as it radiates and radiates. Over a very long time we can see that over a long time it eventually evaporates completely. Now this is where the entire evaporation is being done. But let us remember that Hawking radiation is a thermal radiation. What does it mean? It looks similar to a hot object. It is just a thermal radiation. That means thermal radiation, remember, does not carry any detailed information about what fell inside the black hole. It is purely only temperature which depends on it. So if the black hole disappears completely, all the information about the original matter seems to vanish. Now you might say that, is there any other radiation which actually remembers certain thing? Because I just told that thermal radiation carries no detailed information. Hawking radiation is thermal, so it is just like heating up your pan on the stove. So is there any radiation which carries the previous information? The answer is a big yes. In contrast to electromagnetic radiation, for example, ordinary electromagnetic radiation, say visible light, X-ray, etc., is not usually thermal. It can encode detailed information about its source. For example, from a star's light spectrum, we can deduce chemical composition, its temperature, its velocity, and even the details of its magnetic field, called the Zeeman effect. So electromagnetic radiation is not usually thermal. That means from here we can deduce about the source. The second type of it is called a synchrotron radiation. Now this is a special kind of an electromagnetic radiation emitted when charged particles spiral around magnetic fields at relativistic speeds. So it carries detailed signature of polarization patterns, energy distribution of the emitting electrons, and orientation and strength of the magnetic field. So this radiation actually remembers its source, but the issue is that as the black hole loses its mass, Hawking radiation is purely a thermal radiation. It looks just like heat and it does not carry any information about what falls inside the black hole. So from here what we can get is this, that if I get two black holes of the same mass, that means it will produce the same spectrum, and in no way you can distinguish what fell in it, unlike what I showed you, the atomic or the electromagnetic or the synchrotron radiation. So from here what we can say, if the black hole evaporates eventually, then the information within it will eventually disappear completely. Now that led to a problem. Is this means that the information is lost forever? Because in quantum physics, which is also called quantum theory, the mathematics that is currently believed to underlie all physical processes tells that information cannot be lost. So here we can say that the consequence can be that in what is a quantum theory, information is never truly lost, nor it is truly copied. So at least in principle, you can always determine how a system started, its initial state, and from complete information about how it ends. Now this led to a big problem in the scientific world, and before I go in that, I would like to explain this quantum mechanical phenomena with a kind of an analogy. Now here you can see there are two particles which are shown blue and red, marked as J. And they are moving towards each other. So the arrows are pointing towards each other. They are about to collide. And at this stage, the initial state of the system is very clear. Two identifiable particles, each with definite properties, momentum, spin, etc. Now let us look at phase 2. The particles collide, represented by this purple burst. At the collision point, all the initial information about the particle gets mixed in the quantum interaction. Now we know that in quantum mechanics the evolution is governed by what is called unitary transformation. That means the wave function is designed in such a way it evolves in a way that preserves information. Now at phase 3 what we find is that classically one might imagine some information could be lost in such a violent event. But in quantum mechanics, the evolution, because it is unitary transformation, after the collision, the system produces many outgoing particles. So you can see the blue I jumping over the red J, and they are flying in different directions. But the point is that each one carries bits of information about the original two particles. However, the information is now highly scrambled because you can see one overlapping the another instead of two neat particles J. So, but still you have a messy spray of many. So in quantum mechanics, the evolution is governed by unitary transformation. So while the story looks messy, nothing is fundamentally lost. So nothing is fundamentally lost. This is very important. So what we get from here is that in quantum mechanics, information is never truly lost. Information in is equal to information out. But what Hawking showed is that once the black hole evaporates, because it is a thermal radiation, the information is gone forever. And this clash gave rise to what is called the black hole information paradox. That means there can be two possibilities. The first one is that either our understanding of quantum mechanics is incomplete, maybe information can be destroyed, or our understanding of gravity or space-time is incomplete. Now, this led to almost a kind of a duel, a kind of a controversy fight, or I would say mental fight between a lot of scientists. The first one was Stephen Hawking. Hawking proposed that black holes emit thermal radiation called Hawking radiation and can eventually evaporate. Then comes Jacob Bekenstein, who introduced the concept of black hole entropy and related it to the surface of the event horizon. His work set the stage of Hawking's discovery by connecting thermodynamics and gravity. Then came our dearest Professor Leonard Susskind, who strongly opposed Hawking's information loss idea. Along with Gerard Hoofthe, he developed what is called the holographic principle, and this became central to the idea that black holes do preserve information. And then came Gerard Hoofthe, proposed that information is not lost but stored in subtle correlations at the event horizon, and helped to develop what is called the holographic principle. Well, there are a lot of other scientists, including John Preskill, who proposed the Hawking-Susskind-Preskill bet, and Juan Maldacena. But I would say that if you're really interested to know what happened during that phase, I would suggest you to read this book, The Black Hole War by Leonard Susskind. Now, the book suggests that it is a war, but it is not. Professor Leonard Susskind has shown a beautiful and amazing respect to Professor Stephen Hawking, the way he talks, his problems with his speech, and how he tries to smile and mocks the world entire, and how actually the fight and the mental disarrangement of thoughts beautifully quoted in this book, The Black Hole War. If you're interested, please go ahead and read this book. Now, what actually happened? I would say, who won the war? So the outcome was in 2004 at a conference at Dublin, Hawking conceded the bet he made with John Preskill. That means he agreed to that. He admitted that information is not truly lost, though the mechanism was still unclear at that time, and he famously gave Preskill an encyclopedia as a prize, symbolizing that information returns. And this is the book which is called The Ultimate Baseball Encyclopedia, from which information can be retrieved at will. This was a gift from Stephen Hawking to John Preskill. Now, this actually set the stage for Maldacena's ADS-CFT correspondence and the page curve via the island formula and a lot of other things. So the consensus today is that no information is lost in terms of black hole evaporation. Black holes are consistent with quantum mechanics, and the paradox yet is not completely solved. But modern quantum gravity, for example, holography, islands, quantum extremal surfaces, strongly suggests that the universe respects unitarity. So this was the bet, this was the fight. You can find out a lot of good videos of Leonard Susskind speaking on how he tried to prove Stephen Hawking wrong, and many interesting stuffs on that. You can also read this book which is called The Black Hole War, written by Leonard Susskind. It's a wonderful book to read. So finally, what does Hawking radiation actually tells us? Let us come down to this point. So first we understood that Hawking showed us that black holes are not entirely black. Using the radiation and thermodynamical principle of Bekenstein-Hawking formula, we saw that they emit a radiation due to quantum effects at the event horizon. Second, we also find that quantum mechanics and gravity starts to interact. I won't say starts to interact, but at certain phases it opens a window that quantum mechanics and general relativity can be united. He also showed that black holes do have entropy. That means just like ordinary system, gas, stars, etc., black holes carry entropy in a different way, meaning that they represent a measure of hidden microscopic information. The most striking part of Stephen Hawking's work is that entropy is proportional to area and it is not proportional to volume. So for ordinary classical mechanics, S is proportional to V. This is the usual way we find it because the number of available microstates grows with the accessible volume. But Jacob Bekenstein and Hawking's formula showed something different. For black holes, Bekenstein-Hawking entropy showed that the entropy is proportional to the area, that is the area law. So for normal matter, S proportional to V, entropy grows with how much space particles can explore. But here we can see entropy grows with the boundary of the region, not with the bulk. Also, we found that Hawking radiation tells that temperature depends on mass. So you can see on the left hand side, the smaller the black hole, the hotter it is, the larger it becomes colder. Also, we found that black holes can evaporate by losing energy over a long period of time. Black holes shrink and shrink and shrink and may eventually gradually disappear. This led to the famous information paradox, that if black hole evaporates, where are the information going? And we also find that there is a clue towards quantum gravity because the equation links relativity, gravity, quantum mechanics and thermodynamics, and to some physicists it seems to be a window to a future theory of everything. So all in all, Hawking radiation tells us that black holes are quantum thermal objects. They radiate, they are not black, they shrink, and they challenge our deepest ideas about information and the laws of physics. That's all for today's video. Thank you very much for watching. If you have liked, please do not forget to subscribe to my channel Physics for Students and click this bell icon ringing so that you get all the notification from Physics for Students. You can follow me on my social media handles and write to me for further details at this email ID. Physics for Students will be soon back with a lot of important and interesting videos. See you soon in the next video. But till then, may the good Lord be with you.